Hey John, how you doing?
Good, are you?
Good.
Um, I was gonna I was going to submit my assignment, but I didn't see a spot on Google Classrooms yet.
Oh, that would be my fault. Okay. Sorry about that. To give myself a note to do after this class. Last week's assignment.
Yeah.
Maybe I can do that while I wait for Gideon. So I was kind of looking, it's unsure as to whether or not we're using that makeup day for school. In physics, we kind of thought that we had maybe 3 more weeks of school. I don't know if what's that?
I was under the impression that we had, I'm not sure, but I was under the impression that we had 3 weeks, including today's class. So like 2 weeks from this. I could be wrong. That was just my impression.
See, that's what, so I guess there's confusion. I got to find out because some people earlier were saying that we were going to use the makeup snow day, which brings us to the next week, which.
Oh, so that would be our last week.
Yeah, so I'll have to send a letter to Robin and Randy and stuff and find out, Mr. Heisenberg.
Okay, I mean,
because we either have 3 or 2 weeks, right?
Yeah.
Okay, so I've been kind of going through the rest of this book, looking of points where I want to definitely hit, just so to expose you guys to as much of this calculus as possible. And so we're gonna do stuff from the back of the book today.
Okay. So I don't think we generally do, like, if we were actually going to class, but so if, say, our class next week is the last day, would this be the last day that we're actually getting homework assigned?
Yeah.
Okay.
It would have to be that way. So it's just, just eat, absorb as much as you can of the.
Yeah. Yep.
Yeah. Hey Gideon, how are you?
Doing well. How about you?
Doing well. You hanging in there with the restrictions and new restrictions and everything else?
Yeah. So I have a brother that's in a class pretty near me right now, so I think I might put it on mute so that you don't hear him or anything.
Okay. Well, I don't know when you popped in, but I told John that I know that we either have 2 weeks or 3 weeks left of class. So I'm kind of going through the book and figuring out, more things that I want to hit on or expose you guys to. And we're going to jump to the end of the book. And this is a technique used for, if you go to differential equations, if you go on to Calc 2 into differential equations and stuff, this is where we're going to end up. So this is where I'm going to start today, but it's called partial fractions. And it's lesson 115. So we're going to, like I said, I was trying to go through the book to figure out what to hit. And today we're going to hit all partial fractions. And they happen to be lesson 115, lesson 120, and lesson 126. But we're going to start with lesson 115. And I haven't shared my screen yet, have I? So if we had the integral of du over u, we already know how to solve that. That's the natural log of the absolute value of u plus c. Partial fractions answers the question of solving something of like 4x squared plus 13x minus 9 over x plus 3 and x minus 1. This problem happens to be in the very center of the page, on page 591. So we know what to do when we have 1 over u, or 1 over u plus 1, or 1 over x, or 1 over x plus 3 over 1 over x minus 1. Now we are learning how to solve when we have a complicated numerator over a factored denominator. So once you are able to get your denominator in a factored form, we use a technique called partial fractions. And as long as each one of your factors in your denominator is just one representation of x, as long as there's no squares in there going on, this technique would work, or does work. You would say a over your first factor plus b over your second factor. And in this case, we have 3 factors, so then plus c over our third factor, x minus 1. And we're going to figure out the values of what a, b, and c are going to be so that we can take an integral of it, and it will be a number over a single factor, or a single x variable. And so in order to solve this, we're going to need a common denominator. So if I have a over x plus b over x plus 3 plus c over x minus 1, my common denominator is going to be what I started with. So my first term, I only have an x. So I'm going to have to multiply both the top and bottom by x plus 3 and x minus 1. And then I'll have, that denominator. And then for the second term, b, well, I already have x plus 3, so I'm missing x and then x minus 1. And then for c, I need to multiply the top and bottom by x and x plus 3. And I'm going to go ahead and start simplifying it. I'm going to, just so you remember that it equals this over here, I'm going to need the whole line to simplify it. So I'm just going to take the whole line out and the whole left side out, if that makes sense, and just work on the right side of this equation. So I'm going to multiply out my FOIL out x plus 3, x plus, or x minus 1. So I get x squared plus 3x minus 1, so plus 2x, and then minus 3. And then do the same thing with my b. It's looking at x squared minus x. And then same with the c. X squared plus 3x. And then you agree, if I have the same denominator on both sides, if I take that whole denominator and multiply to the other side, it's going to cancel out. So basically now my numerators are equal to each other. That was, do you understand? Does that make sense? That was the whole reason for getting common denominator on both sides. So that, if I had like 1 over 3 equals x over 3, those 3's are going to cancel. So basically now I just have my numerators that are equal each other. I'm going to still do some simplifications. So I have ax squared plus 2ax minus 3a plus bx squared minus bx plus cx squared plus 3cx. Once I have it all simplified out, I'm going to get all my x squared variables together, all my x's, and then all my constants together. So I'm just going to associate everybody around, move everybody around. So I have ax squared, I have plus bx squared, plus cx squared. And where's my x's? I have a plus 2ax minus bx plus 3cx. And then where's my constants? I have a minus 3a. And that's my only constant. I'm going to factor out the x squared from these terms. So I got a plus b plus c. I'm going to factor out the x from these terms. 2a minus b, oh, plus 3c. And then I just have that constant again. Now I'm going to use this technique that I'm not sure if you've ever seen this before, but I have seen this technique used on the ACT and SAT a lot. But it comes from learning partial fractions, which is really interesting, but it's a really powerful technique. So if I have 4x squared plus 13x minus 9 equals, and then I have the a plus b plus c x squared plus 2a minus b plus 3c x minus 3a. What you can do is you can set the coefficients in front of the same variable equally to each other. So I can say for the x squared terms, I can say 4 equals a plus b plus c. Those are the coefficients in front of the x squared terms. In front of my x terms, I have 13. 13 equals 2a minus b plus 3c. And then in front of my constant, I have a negative 9. So negative 9 equals negative 3a. And then typically when you're doing these, you're going to be solving them backwards. I have one variable here, but I have got 3 variables, 3 unknowns. And so I start solving it, and I have negative 3a equals negative 9. So a is going to equal 3. And then I go up to the equation above it. 13 equals 2a minus b plus 3c. And I'm going to have the other equation as well that I'm going to need to use. 4 equals a plus b plus c. And I'm going to substitute for a 3. I should have done that first. So 13 equals 6 minus b plus 3c. And then on the other side, I have 4 equals 3 plus b plus c. So now I'm down to 2 equations and 2 unknowns. I know what a is, and now I need to either solve this by elimination or substitution. And it looks like I can do an elimination since negative b is in both of them. So I'm just going to line them up for elimination. So I'm going to bring the first equation, 13 equals 6 minus b plus 3c. So I got 17 equals 9, the b's cancel, plus 4c. Bring the 9 over, divide by 4, and then I got c equals 2. And then I can use my value for c to find out what b equals. So 13 equals 6 minus b plus 3 times c, and c is 2. 13 equals 6. 6 plus 6 is 12. B equals minus 1. And so now that we have a, b, and c, we can go back to that original equation that we had of a over x, b over x plus 3, c over x minus 1. With a equaling 3, I got to flip the page, so I got to remember this. 3, 2, and negative 1. Nope, I'm going to do 3, negative 1, and 2. A, B, and C. And I'm flipping the wrong way. We'll go this way. So we had 4x squared plus 13x minus 9 over x plus 3, x minus 1. And then we split it up to a over x plus b over x plus 3 plus c over x minus 1. A was 3, b was negative 1, and then c was 2. Actually, if you look in the middle of the page, they skipped all those steps that I just did, and they just went right from this step to this step. You got that, right? So just be careful that if you look at the this problem, like I said, it's right in the middle of the page on 591. They just went right from here to that equals here. And so you have to do all that middle stuff in order to figure out those variables of a, b, and c, or all the steps I just did on the other page. And so if we were going to take the integral of this now, it's going to be the same as taking the integral of the partial fractions. And so now we have 3 integral dx over x minus integral of dx over x plus 3 plus 2 integral dx over x minus 1. So we just simplified the original problem that we had with a complicated numerator into 3 partial fractions. And now we can take the integral of these because we know dx over x is ln x. And so we're looking at 3 ln absolute value x minus ln absolute value x plus 3 plus 2 ln absolute value x minus 1 plus c. And that is partial fractions. And like I said, it's a technique. You can use it anytime you have 2 sides of an equation and there's exponents that are the same. You can set all the coefficients equal to each other to solve it. But let's look at number 1 here. That wasn't even 1. The next page, 115, problem number 1. We're integrating dx over x squared minus 1. First thing you need to do is factor out that denominator. So this is difference of perfect squares. X minus 1, x plus 1 gets you x squared minus 1. And then in our partial fractions, we're looking at a over x minus 1 plus b over x plus 1. We're going to solve it the same way. We're going to want to get the common denominator. So for a, I'm going to need to multiply by x plus 1. And then for b, I need to multiply by x minus 1. To get my common denominator. And then I'll have my numerators are equal. So I'll distribute the ax plus a plus bx minus b. We have 0 for our x terms. We have a plus b on the right side. And then our constants is 1. And we have a minus b. So from the first equation, I have a equals negative b. And I'm going to substitute that into the second equation. 2 equations, 2 unknowns. So 1 equals a minus b. 1 equals, instead of a, I'm going to put minus b. 1 equals minus 2b. And then b equals negative 1/2. And then if a plus b is equal to 0, then a is going to have to equal positive 1/2. So now I'm integrating 1/2 over x minus 1. Doesn't need any paper. When you integrate that, you're going to get 1/2 ln x minus 1 minus 1/2 ln x plus 1 plus b. I chose a different a and b than the book did. I was just looking how the book did it. I guess they did x plus 1 first over a. So my a's and b's are swapped. If you're following the book. But you still get the same answer. Any questions on that so far? I know I skipped over a lot of steps on that first problem, or that last problem.
Are we gonna do example 2 as well?
Yes, we'll do example 2 as well.
Okay.
Let's do the 2. Just wish I had more room. These are too long. I wonder if 115(2). All right, so we're integrating 2x plus 3 over x plus 2, x minus 1. So we're going to do our partial fractions. We're going to say 2x plus 3 over that denominator that we just had. As long as there is no squared terms in here, and there's no repeated squares, those are going to be coming up next. We can just do a over the first factor plus b over the second factor plus c over that third factor. And then we're going to get a common denominator. So the left side's still going to equal 2x plus 3. And when we get that common denominator, the denominators will cancel each other so that the numerators are going to equal. So now a has to be multiplied by x plus 2 times x minus 1 for that common denominator. B has to be multiplied by x times x minus 1. And then C needs to be multiplied by x times x plus 2. Is it okay skipping the denominator step? Are you okay with this step?
So basically you just found the common denominator and then multiplied both sides by the denominator?
Yep. Yeah, so
Okay.
yeah, so if you had like 1/3 equals, I don't know, x over 3, you multiply both sides by 3, those denominators are going to cancel. So whenever you have a common denominator, it means your numerators are equal. So that's the whole trick in partial fractions. So I have to multiply each term though in order to get the common denominator. So does that make sense how I did that? Like a had to be multiplied by the terms that are missing in its denominator. Yeah. Okay. And then I'm going to simplify. So I'm going to FOIL out what I can FOIL out. So I've got x squared plus 2 minus 1 plus x minus 2. And I got x squared minus x. And then x squared plus 2x. And then I'm going to factor it out again. Factor out my letters. So then I have ax squared plus ax minus 2a. And then factor out my b, or distribute the b, plus bx squared minus bx plus cx squared plus 2cx. And then I'm going to group my x squared x's and constants. So I'm going to pull out of the x squared terms, and I'm going to be left with an a plus b plus c out of my x squared terms. And then if I pulled out an x, I'm left with an a, where's another x, minus b plus 2c. And then where's my constants? I have a constant of minus 2a. Is that my only constant? X. Yeah, so I only have one constant, the minus 2a. Now I am going to pull coefficients, equal coefficients out. So I'm going to get all my x squared terms. On the left side of the equation, I have 0 x squared terms. On my right side of the equation, I have a plus b plus c. So I'm just making my coefficients equal. And then I'm going to pull out my x terms. On the left side of the equations, just the coefficients of my x term, I just have a 2. On the right side, my coefficients are a minus b plus 2c. And then I'm going to work on the constants. On the left side of the equation, I just have a 3 for a constant. And on the right side of the equation, my constant's negative 2a. And then I'm going to start solving, and it's typically the bottom up. You go from, I can get a really easily. So a equals 3, negative 3/2. And then I'm going to use a in both of these equations, and I'm going to eliminate b because I see that I have one positive and one negative. So I'm going to rewrite that first equation. 0 equals, well, instead of a, I'm going to put -3/2 plus b plus c. And then that second equation, I have 2 equals, and instead of a, I'm going to put -3/2 minus b plus 2c. And I'm going to eliminate one more variable, which is b, so I can solve for c. So I add them up. 2 equals -6/2 plus 3c. Add 3 to both sides. So I have 5 equals 3c, and c is going to be equal to 5/3. And then I'm going to use a and c to find b, and substitute in one of the equations. So 0 equals -3/2 plus b plus c. What was it? -9/6 plus b. 10/6. I don't know. I always have to get a common denominator. 1/6 plus b. All right, so b equals -1/6. All right, so I have a, b, and c. Now I gotta flip it over. Is it okay to find a, b, and c so far? Once we have that?
I'm not exactly sure how you found A, B, and C.
Okay, so these were my, are you okay with these equations right here? 3 equations and 3
Well, not exactly.
Okay, so this is a really, like I said, this is something that is new, and it is a really powerful tool. Something you're gonna not wanna forget when you get into any other math classes. But whenever you have like a polynomial on each side of your equal sign, you can set the coefficients of the same exponents equal to each other to solve it. So if I have 2x plus 3 on the left, right? Are you okay with this line here?
Oh, wait a minute. Yeah, so those 3 equations, those are just the first, second, and third. Well, the first and second things in parentheses, and then the -2a.
Is my constant, right? There's no x with it.
Oh, yeah. Okay.
So I'm just setting the coefficients equal to each other. So on the left side, I don't have any x squareds. So my coefficient's 0 for x squareds. But I do have x squareds on the right side of the equations.
Wait. So how did you get the 0, 2, and 3?
0, 2, and 3. Because there's 0 x squareds over here. There's 2 x's, and then there's a 3 for a constant. It all came from my numerator. My numerator has 0 x squareds, it has 2 x's, and then it has a 3 for a constant.
Okay.
So 0, 2, 3, okay?
Yeah.
The left, okay, so that's the left side. The left side comes from the numerator, and then the right side comes, well, from our partial fractions. So A, B, and C okay so far? That step. So that means we rewrite our integral now. We had 2x plus 3. I will never complain of a small whiteboard again. Did I say that already? Because paper is so much smaller. So we had that as our original, and then we broke it up into A, B, and C. So our A was -3/2 over X. Our B was -1/6 over X plus 2. And then our C was 5/3. And we're going to be running out of time here soon, over X minus 1. So basically, doing partial fractions is a way to rewrite our initial or our original equation, our original polynomial. So our original polynomial, to integrate it, we do it to partial fractions, and now we can just integrate each partial fraction. So we distribute our integral and dx into our partial fractions, and we're looking at the integral of, well, I can pull out the 3/2, the constants. -3/2, then dx over x. And I pull out the 1/6 and distribute that integral dx over x plus 2, pull out the 5/3, integral dx over x minus 1. And now we are able to take the integral, -3/2 of ln absolute value x minus 1/6 ln absolute value x plus 2 plus 5/3 natural log of x minus 1 plus c. So that is one type of partial fractions. And I got 5 more minutes. We'll see how far we get for the other type. But that's the type where you have in your denominator in a factored form where there is no x squareds and there is no repeating factors. We're going to move on to lesson 120. Oh, let's get work for that page. Sorry. For practice problems. So 115. I would say just do the practice problems for the lessons that we've done so far, because I haven't pulled them out yet. Because we skipped, obviously, a lot to get to 115. So I'm looking for the ones that are at 115. Number 6. 6 and 7 are the ones in this one. And that's probably all that you'll be able to do from this lesson. But you know what? Let's look at lesson 116 and pull out stuff from this stuff. So wait, this is lesson 115. This is the bad part of skipping. Where's the 115 problems? They don't have any from lesson 115? Oh, they do. Okay. So from lesson 116, number 7 and 8. Lesson 118. Oh, did I skip this? No, lesson 117. Sorry. Looks like there's only one, number 18. And there's 2 in lesson 118. So homework is kind of all over the book. Sorry about that. 12 and 13. But just to get practice on doing partial fractions. we'll just do lesson 115, 1, 3, 6, and 7, 116, 7, and 8, 117, 18, and then 118, 12, and 13. And I'll have to put the homework in for last week. Sorry about that. All right, let's move to lesson 120. It's still partial fractions, but now it's in the form of duplicating a factor. So if we have like 1 over x, and then if we have a factor that's duplicated, like x plus 2 squared, the way that is handled in partial fractions, or to separate that, you would say a over x still, and you would still say b over x plus 2. But then to handle the duplication of a factor, you'd say c over x plus 2 squared. And then you would apply the exact same steps that we've done before, get a common denominator, set the numerators equal to each other, well, the coefficients of like terms equal to each other, and then solve for a, b, and c. But this is the whole new step that we did not do yet, was setting up our partial fractions. So let's look at number 1. And we're going to integrate 4 over x times x plus 1 squared dx. So our polynomial is 4 over x, and then we have a term that is duplicated, or one of our factors are duplicated. So that means we will have a over x, b over x plus 1, and then c over x plus 1 squared. And now we want to get a common denominator on the right-hand side.